Right, you might have noticed in one of my previous videos there was something missing from my keyboard. Have you spotted it? Yes, it's the shift key. No prizes for that one. The reason it's missing was I think the T key was broken. It was making it quite difficult to use the keyboard, so I sort of swapped the keys over. Now, the keys are really strange. In the manual, they're just like normal key switches, just a contact closure. Yeah, fair enough. And let me just get this out of the way, show you something. The back of the keyboard matrix, as you can see here, there's actually 4 connections to each of the switches, which sort of immediately sent sort of alarm bells ringing. I tried over and over again with a sort of DVM trying to make some sort of sense of it, and couldn't. And in the end I thought, oh, I'm going to have to take the switch out anyway to swap them over, so I took them out. And the switches are really curious. I think this is this way. This one here, this is the actual switch itself. You can see the 4 connections on the bottom there. Now it looks fairly innocent until you tug it on the bottom, and then this pops out. It's quite intriguing. It's actually a hall sensor. And inside the switch on the plunger is a magnet. So I'll try and demonstrate. Let me see if I can. There you go. Proof of the pudding. That needle sort of hanging from the magnet in the plunger. So all very odd. There seems to be a couple of different versions of this. This one, I think, which way up is it? It's that one there. You probably can't see it because it's engraved. But the other type is this one. Now you see this one. I'm not sure if it's engraved or I think it's just stamped in white or painted in white. So that's the main difference. But in addition to that, underneath, and if you can see it shining, there's a really annoying little retaining clip, which isn't really needed for this application. Luckily they're glued in, and over this sort of period of time, since the, I don't know, late 1980s, the glue's failed, so you can get them out by just giving them a bit of a tug, and you end up with this little annoying retaining clip and another hall sensor. Slightly different this time. It's green, and you notice the actual little hall device or the semiconductor part of it is actually much smaller if I hold them together. You see the blue one out of my one's much bigger than the green one on the right. So that's what's in there. It's quite interesting. They're made by a company called Micro Switch. You can see that on the PCB. It's also on the keyboard matrix there as well. And guess what their claim to fame is? Have you guessed yet? Well, they invented the first ever solid state keyboard. So there you go. That's why it's got hall sensors in it. Right. So that's the history lesson out of the way. Depending on how many switches you've got to repair will depend on how you get them out. If you've only got one to replace, as I have on my keyboard, then you might as well just lever them out basically. So just unsolder from the PCB, turn it over so that this is facing you, and then you just need to push in these 4 clips. Now the best thing is to get 4 small screwdrivers like this, push one into each corner, and that will unhook the clip, and then you can just wiggle it out. in the end, I didn't actually have 4 screwdrivers. I cut up some little bits of very thin metal plate and I pushed them down. I pushed it forward with a screwdriver and pushed a little bit of metal plate in the gap, and then managed to pull it out just with a little bit of a wiggle. If you've got what I presume are the earlier switches, and you've got to repair loads of them, as I have on this one here, this is in the right state, this one, you can just pull the whole lot off, because as you saw here, this, literally that little PCB just pulls out, and as you can see here, you can see all the little PCBs still on the keyboard matrix. To do that, all you need to do is on the back, see all these little metal sprigs here, you just squeeze those together to release them. They poke through the little holes here on the top, and there's also, depending on which keyboard you've got, there's either 3 screws along here, or there's some really annoying little plastic push clips which you can get out if you wiggle them long enough. Don't go too mad, otherwise they'll snap. But mate, to be fair, you can always replace it with a screw. If you've got the later type switches with the annoying retaining clip in there, that becomes a bit more of an issue, and that's what this one was like. What I ended up doing in the end is I unsoldered the ones in the middle, and then just sort of wiggled the PCB around till the glue failed, and then I pulled it off. So you see all the inserts are missing in the middle, but they're still around the outside. So that's how I got mine off. But you don't really need to do that unless you've got to replace a whole load of them, which is probably fairly unlikely. Don't know what's happened to this one. This is one I've been given to repair, and maybe I had an overvolt or something, or the switches were a bit defective, but loads of them are busted on here, so I had to take the whole lot apart. Right, so that's the intro. What we'll do, we'll go over to the PC and I'll show you what these things actually consist of and how I propose to replace them. Okay, so this is what Intel tell us is in the keyboard. As you can see, there's no sign of any hall sensors here. This is a conventional keyboard, so these are just ordinary key switches. The overall circuit is the same though, so don't worry about that. So we've got a keyboard processor here. It's driving a 4 to 16 line decoder for the scan, and it's detecting down here. So what happens is, when it's scanning a line of keys in this direction, one of these lines will go low. The detection lines are pulled up through this resistor here, and obviously whichever key is pressed joins the scan to the detect line. So if this key here was pressed and it was scanning that row, that would pull the end of that resistor low down here, and the keyboard processor would detect a low there, and it would know, because it's scanned that row and it's detecting on this line here, it's that key. Also worth noting at this point is that there's a maximum of 8 keys in each row. So we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's look what's inside the actual key switches we've got. If I can find it. Right, here we go. This is what is inside that module that we saw over on the bench, or at least a sort of representation of it. Clearly we're not going to be able to recreate this, or not in the space that we've got anyway. So what I've had to do is come up with a different plan. So what I've come up with is, we go to this one, these little red circles represent the holes on the keyboard PCB. So we've got 0 volt at the bottom, 5 volt at the top. We've got the scan from the 154 on the second one down, and we've got the detection. See where the resistor's going up to 5 volt there on the third one down. Now, what I've done is used a standard hall sensor. See the picture of it here. It's 5 volt normally, and I've used the 154 to create a virtual ground. So this is the 0 volt on the hall sensor going through here. So when the scan line goes low, as it will be when it's scanning that row of keys, it will create a virtual ground and power up the hall sensor. Once the hall sensor is powered, it will then, if, you know, assuming that a magnet comes into its vicinity from the key press, it will close its output, or it will pull its output down low via this wire here, and it will pull this resistor to 0, and that will go off to the keyboard processor just as it did on the original diagram. So that's how I've got around the problem. There is an issue, however, that this is going to draw some sort of power, because the original devices obviously took their power from 5 and 0. On here we're actually pulling power this way, so we're using the sync capability of the 154. Now if you're just replacing 1 or 2 keys, it's not a problem, because it will sync 16 milliamps in total. Bear in mind that there could be up to 8 of these, assuming you went the whole hog and tried to replace a whole load of keys. So if you went that far, they draw about 2.5 milliamps when they're sitting there doing nothing. That would net you 20 milliamps, and there'll be another 2.5 milliamps on top of that if the key's pressed. So my solution to that is, if you've got to replace a hell of a lot of these keys, as I've got to do on the other keyboard, then you can change this 74154 to a 74 HCT 154, which is a CMOS chip, which has got a sync capability of 25 milliamps. That should keep us safe. So just bearing that in mind if you're replacing loads and loads of keys. I think that's probably unlikely. An obvious solution to this would be to use the modern micro power devices. There's a problem, unfortunately. Let's just have a look at the device I'm going to use. Right, this is what I'm proposing to use. Plenty of these available on eBay, fairly cheaply. Now, this device, let me just scroll down to the package. Where is it? Here it is. Right, okay. So I'm going to use this package here. Now, this is what's called a unipolar Hall effect sensor, or switch in this particular case. That means a south facing magnet needs to come in close contact with this surface here. Now, the micro power devices, of which I've tried 4 different ones, are at least the ones you can obtain easily, are called omnipolar. Now, omnipolar devices switch with either end of the magnet on either side. So whereas this will only switch with a south pole magnet on this side, an omnipolar device will switch on this side and this side, north or south. And it also appears that they're particularly sensitive downwards as well, you know, on the top of the device. And remember, our magnet is actually hanging over the top here, and for that very reason I've had to go back and use this sort of conventional device. And another thing to note is that the magnet in the keyboard switch is south facing, so the beveled side of this needs to face the magnet. Right, so hopefully that's clear. Let me just go show you my solution I'll show you the picture. Now this is what I'm going to do. I've converted this effectively into a surface mount device, and the beveled sides are on the side you can't see facing the PCB, obviously because the magnet behind it is south facing to make it trigger. I suppose the obvious question is, well, why didn't you use a surface mount device? The problem with it is yes, a surface mount device would make it much easier, but the surface mount devices are all south facing as well, and to make the surface mount device work, you'd have to turn it upside down and squash its leads in the other direction, which might be quite painful for it and is likely to break all the leads off. That's why I've stuck with a conventional device which is much more robust, and we can bend the leads easier. So that's my sort of solution. This is the original device, or one of the original devices. You'll notice that this is actually longer than this one. However, if you look carefully, you see there's a notch in that lead there. That's the actual depth of the sensor. This is where the PCB is effectively. The PCB sort of sits underneath that notch. So there's room inside the switch for this to fit. But when we change these pins over, we need to cut a bit off the end here, so this notch lays level with the this PCB, so it'll fit into the keyboard PCB. Right, so that's the plan. So what we'll do is we'll try a real keyboard, and I'll show you how it works. Let me just show you a picture of how it looks in the keyboard, because it will be difficult for you to see it on the real thing. So there you go. That's what it looks like when it's soldered into the keyboard matrix. You see how low it is. It's a bit confusing, isn't it? Because it looks like it's slightly lifted, but it is completely level with the PCB, and the key switch itself will fit over the top. So that's what it looks like when it's in place. Right, let's have a look at assembling the modules. The boards will come quite square or oblong, whichever way you want to look at it. You'll need to bevel the tops a little bit, just here and here, otherwise they won't slide into the switch properly. So you obviously check that before you start. I'll just slide that one in there. There we go. Just make sure it goes all the way in. There are some little raised bits on the switch there, so it won't go right the way in, but as long as it lays flat on the bench, it should be fine. Right, let's get that out. Pull him out. Now, the little Hall effect sensor, we need to turn that into a surface mount device, so we're going to have to push its leads down a little bit. The easiest way I've found is to use a fairly wide screwdriver blade, and hopefully if you get fairly close to where the leads are and push down gently, you should better get a little sort of a Z bend in there. There we go. Don't know how easy it is to see that on the camera, but everything's so small, it's never a problem. Right, what you need to do then is figure out how long the leads need to be. So, okay, so if I get my cutters, I'll trim those off. Looking about there, I reckon. Let's try that first. See what that looks like. Okay. I think that looks okay. Let's just check it in the... It looks pretty flat. thing to do is to sort of hold it sideways and then make sure the leads are making good contact with the board, otherwise you'll have trouble soldering them. That seems okay. Right, so let's give that a bit of a wipe over before we start. So a little bit of IPA. Okay. Now what I've got a little jig that I made out of a few sheets of sort of thin plywood. You probably don't need to do that if you're only doing one, but since I've got to do a load, it's quicker for me to do it like this. So the way it works, so you push that in there, hopefully everything lines up. Just checking from the side to make sure it's really flat, which it looks like it is. So put some tape on there, make sure nothing moves. Let's put a bit more tape on the board actually, so I think that's moving. Right, okay, so hopefully everything's fixed in place now. So we'll get some flux. Definitely need to use plenty of flux on this, otherwise you will have some trouble. Okay, soldering iron over. The best thing to do is just put a little tiny bit of solder on the tip, just that clean, and let it sort of run in, because actually soldering it could be quite a problem. Hopefully the flux should do the job for us. So there we go. That's that one. It's just a case of repeating that for the other three. Seems to be flux. I'll put a bit more flux on there. Okay, hopefully that's done the job. There you go. A bit of a clean up. Right, there we go. There's the completed module. Try and get my fingers out of the way so you can see it. There you go. That's what it should look like. If you look from the side, it's laying nice and flat there. Okay, so that's that bit. So what we need to do now is get the legs off of an old module. If we bring that in, there so you can see it. Right, hopefully you can see that there. Right, so the easiest way is just to make sure you've got a bit of solder on your tip, so you've got some sort of conduction to the pins on the module. So I'll put a little bit of solder on there, and they should, in theory, just float off. So I'll get rid of my tweezers. Hopefully. There we go. So it takes a little bit of heat, so make sure there's some solder on your iron to conduct the heat. Put a little bit more on there. You can always increase your iron temperature a bit if they don't want to come off, but they should come off fairly easily. There we go. And while you're at it, you turn it over, just give the other side a bit of a clean up. Obviously you're gonna need a fairly clean surface to solder back onto the little module, so I'll do that one as well. You can always go over a bit of solder braid if you really need to, but should be alright. Okay, so that's that bit. Let me set up for the next stage of the process. Right, next stage of the process, let me just give me tweezers. Hopefully you can see what I've done here. I've got the module on the right, and I've turned one of the little blank PCBs upside down just to give me a level surface. This is the pin I'm going to try and transfer. You might have to trim a bit off the end, as I said before. That sort of indentation or ledge or whatever you want to call it needs to be at the bottom of the PCB, otherwise it won't go properly into the keyboard PCB. So the first thing to do is to tin the pad, solder in, end one, solder on there. Right, now again, put plenty of flux on there. So obviously we can't get any solder behind here, and we're going to rely on the flux to actually do the work for us. So push the lead into position where it needs to go, probably about there. It's not that critical, but as long as it's in the general area. You can always bend it a bit. I'll hold it down with this little block of wood. And get the iron on top, and that should do it. Right, there we go, and you just got to repeat that with the other four. The only thing to remember is that little notch on this side, that they all need to face towards the centre to get the spacing right. So I'll do the other ones. I won't do it on camera because it will take ages, and when I've done that I'll come back and have a look at the result. Right, that's what it should look like when it's finished. I've already got one soldered into the keyboard PCB. I've upgraded the 154, let's just get it into shot here, to a 74 HCC 154 as we discussed earlier. The module itself is here. I'm not sure how well you can see it actually, but there it is anyway. So we'll go over to the MDS, plug it in and see what happens. Right, okay, we're over at the MDS, everything powered up. What I'll do, I'll just show you one of the working modules first. So these are the four holes on the PCB. We've got 5 volt on the top. That's the detection line with the resistor up to 5 volt. That's the drive from the 154, the scan, and we've got ground on the bottom. So if you put a key on there, let's just see what happens. Hole, pop them on there. Right, now as I press the key down, you see the logic probe flashes. There we go. So that's sending a signal to the keyboard processor now that key's pressed. Right, and we'll go over to our new module, which is this one here. We'll put the key on top of it, and again get on the scan line. Further up so you can see it. There we go, I think. Right, press the key. Well, still not on there, am I? There in a minute. There we go. Right, press the key, and again we see the flashing of the probe. Right, now of course this is no good unless it actually produces the correct key. So let's go up and look at the MDS screen, and I'll press the key and then we'll see what happens. There we go. Right, I'll press the key and hold it down first. Right, so there we go, number 9's appeared. Now I'm holding the key down, now I'm going to release it. So we're just checking for key bounce here. So every time I press the key, it's down, up, down, up, down, up. So we're not getting any key bounce or anything. Obviously, you know, the magnet's passing backwards and forwards past the hall sensor, so we only want it to sense on the downward stroke and not come off on the upward stroke. So there you go. So it seems to be working okay. So that will do it for this video, and if you liked it, give me a thumbs up, and I shall see you next time.